Hello, everyone, and welcome to this month's Department of Energy Python Exchange. My name is Cameron Riddell, and I will be your host this evening, afternoon, or morning, depending on the time zone that you live in. And I think today is a most reasonable time to say that because we are joined by Dr. Hans Dembinski, who is joining us from Germany. So it is quite late there in his time zone. As you all may know, though, our goal is to have Python thrive within the National Lab system and associated research sites. In support of that goal, we are joined by Hans, who is here to share with us a lot of his work in Python and how we can use it to fit various models and do it rather quickly, might I add on top of that. So Hans, we are very excited to have you join us and are very eager to hear all of the things that you have to share with us. But before we get into all of the fun that is Python and its coding and how we use it in our lives, I want to remind everyone of a few key points about these exchanges. This call will be recorded, edited, and posted online. As a consequence, please be conscious of the information and the questions that you may ask to ensure that you're not accidentally sharing anything that's privileged or requires clearance. Additionally, as you all know, we are a growing community and we would love to stay in touch with each of you. If you want to be kept up to date with our monthly exchanges, please sign up for our mailing list, which you can find on our website. That's meetup.doepy.org. And you can additionally find recording of past exchanges on this site, as well as a recording of today's exchange once it has been edited. For those of us who have never joined us for an exchange, I would like to share with you that we typically break these exchanges down into 4 parts. First, we'll introduce our fantastic lineup of hosts and guest panelists so that you may all get to know them as well as their respective fields and backgrounds. Second, we'll kick off into a coding activity where we'll ask some fairly applied questions to our panelists to elicit some practical discussion about best practices in software development and where they fit into the world of academic or scientific research staff. Third, we'll turn things over to Hans, who will share some prepared remarks on Python. And then to wrap up, we'll have a discussion, a Q&A brought about from our guest panelists. And for everyone joining us in the audience, this will be your chance to ask questions and engage with our panel to help us all understand where Python fits into the life of a researcher. Now, let us go ahead and we'll dive into our introductions. For our introductions, we like to play just a brief game, one question game, I might add, of Ask Me About. So how we play this game is I'll simply go through our host and guest panelists and say, you know what, Andy, or asking myself, Cameron, what is it that you're an expert in? What do you want to hear questions about today? And so I'll start off first in saying, hello, everyone. My name is Cameron Riddell. And while I am not affiliated with a specific lab, I do have a background in academic research as I studied cognitive sciences in graduate school. For today's exchange, I would love to discuss any and all questions related to Python as a whole, or specific concepts and uses in Python's vast scientific computing ecosystem relating to tools such as NumPy, Pandas, Matplotlib, and more. And so to follow up, Andy, what is it that you're an expert in, and what types of questions do you want to field for us today?
So I would say I'm an expert in using Python to analyze scientific data of various forms, arrays to scalars using NumPy, Pandas, and something like Xarray or SIP. I'm really interested in helping ask questions about people getting started or teaching other people that know very little Python how to get the most out of the least amount of code they can write.
Excellent. Thank you so much, Andy. We are very happy to have you join us. Next up, we are also joined by Tanny Chavez. And Tanny, I see that you are at a different lab than Andy. You're at the Lawrence Berkeley National Lab. But Tanny, what is it that you consider yourself an expert in, and what types of questions would you love to address for us today?
As a research scientist at the Advanced Light Source, I mostly work on developing machine learning techniques or implement, in this case, these techniques to a larger scientific community. So the type of questions that I would love to receive will be more in terms of how to make these tools available to a larger community that may or may not have the expertise in ML in order to be able to use these tools.
Fantastic. I think that's such a noble goal of making computing accessible to everyone, not just from a physical standpoint, but also from a conceptual understanding perspective. I know personally, going into graduate school, one of the most daunting things is you're supposed to become an expert in a field, and then somewhere along the way, they're also like, you know what, you have to learn a lot of programming as well. You're thinking, wait a minute, how do I have to do all of this in just such a short time? But Tanny, thank you so much for joining us. I'm very happy to have you here. Next, we are joined by our guest panelist, Dr. Hans Dembinski. Hans, I see that you're a research fellow at the Max-Planck Institute for Nuclear Physics. Can you tell us a little bit about what you consider yourself an expert in and the types of questions you would love to hear today?
Yeah, so in the meantime, I changed to the TU Dortmund, so it's a university in Dortmund. But what you said was correct before. So I'm a statistics expert, and I do most of my programming in Python nowadays. In the past, I was also using C++. I'm very concerned, or try to get my algorithms run fast, because I believe that speed is quite important. You can do more checks, and you can use more advanced techniques when your code is running fast. So that will be something that I would like to get questions on, and maybe also about interfacing different languages with Python. You can ask me about, or statistics, of course.
Yeah, fantastic. And so, Hans, since you are a statistics expert, do you find yourself working on just a single project at a time, or do you often work with multiple different projects and multiple different individuals on their projects?
Yeah, so right now I'm a sub leader in our research group, which is run by the professor Johannes Albrecht, and I'm the supervisor of the subgroup within that group, which consists right now about 4 students, and so I'm involved in all their projects, which are concerned with different analysis of LHCb data.
Fantastic. Well, it sounds like you have an amazing position, being able to work on so many projects, and I'm very excited to hear what you have prepared for us. Now,
Thanks.
Of course. Now, I want to share with our audience that you too can become a host panelist. All you need to do is reach out to us at doepy@dutc.io. If you email us here and say, I'm interested in becoming a host panelist, then you will absolutely have your turn up here on stage talking about Python and being able to interact directly with our guest panelists each month. Now, let us jump right into our coding activity. The coding activity that we'll be playing today is called My First Time. And here's how you play. Python 1.0 was released the year that I was born. But many of us have not been using it that long. I sure have not been using Python since 1994. I started Python in the late 2.7 days. Now, we want to get to know our panelists and our audience more by finding out when and how some of their programming firsts were. So each round will go like this. Our panelists will be presented with statements about the first time that and we'll leave that to fill in the blank. Our panelists will provide the approximate year that they completed this task and share a fun anecdote about their experience. Panelists will be scored, not really, on the specificness with a bonus point for fun anecdotes. So let's dive into our first round. Round 1, for loops. The first for loop I ever wrote was in, and Andy, why don't you let us know what the first for loop you ever wrote was and when that was?
Yeah, that was Visual Basic in 2004. I think that's right. Yeah, using all the help functions.
Using all the help functions. Fantastic. And Andy, what task were you trying to accomplish with this for loop, if you remember?
Yeah, I was trying to sort a bunch of assay results for biological compounds and understand when the calibrants were failing over time.
Awesome. It's amazing to hear that you were using automation in your analyses in that way. even though it wasn't with Python. I'll forgive you this time, but Visual Basic, gets the job done. And Andy, I see that you're also joined by Hiran there. Hiran, can you tell us just very briefly a little bit about yourself? I know that you work at the Berkeley National Lab, or the BNL, and can you tell us just one very quick sentence of what is it that you do and what types of questions would you love to answer today for us from our audience?
So I work at Berkeley National Lab, like pointed out. So we have this data science and systems integration group. I'm part of that, and I work on implementing new features and functionalities for the Beamline scientists like Andy here, and I've worked with her a lot. Yeah, and then in terms of the type of questions, I guess anything about Python.
Anything Python, data science, or machine learning. Fantastic. And Haran, what was your first for loop that you ever wrote?
It's funny because it's also Visual Basic. I remember Visual Basic 6.0, and it was around the same time as well.
It wasn't on the same project as Andy, though, was it?
No, I wasn't even in this country back then.
Fantastic. Well, thank you so much for sharing. Tanny and Hans, would you like to share with us what your first for loop experience?
I think mine might have been in a class, and I think it may have been in C, and I'm pretty sure it was on paper. So I don't think I was even writing down that in the machine yet. I think it was definitely on paper. I believe that what we're being taught about, what was the thought process, how to first kind of like understand how to structure our code before jumping onto like doing it practically. And I think it was just to find prime numbers between a range of numbers. So I think that's as much as I remember about it.
Very, very fun. Now, I have to ask, since you were starting on paper, did the code that you wrote on paper actually work once you wrote it on a computer?
Oh, no. It was my first time writing code, and I think that was exactly the very first statement that we were being taught about. So I'm pretty sure it did not. After probably the second try, it did work.
Fantastic. I think we all have the same startup issues getting code to work the first time when we think it should. But thanks so much for sharing, Tanny. And Hans, would you like to share with us your first for loop experience?
Yeah, I don't really remember when that was exactly, but I think the first time I got in contact with a programming language ever was already in school when I was maybe 17 years old. So that would have been, yeah, somewhere around 1998. And yeah, I guess at the time it was BASIC. Then later I wrote a little bit of code in C. I had a book to learn C by myself. And then at some point in the early 2000s, I was getting started with Python. And that was the language I like best out of all the three.
Fantastic. So you started Python in the early 2.0 days then?
That's true.
Fantastic.
Yeah, quite different at the time.
Yeah. And so I do have a lot of questions about what you miss about Python too, but I think we should jump into.
Well, I don't miss anything about that. Python is much better.
Yeah, I'll agree. Let's jump into our next round. The next round is our first line of Python. The first line of Python I ever wrote was in. And let's go down our guest panelist or our list of panelists. So Andy, what was the first line of Python if your first for loop was in Visual Basic?
I guess it was in like 2014. Yeah. And one of the first things I did was try to use a for loop to sum an array, and that took forever.
You were just working with built-in Python ints, floats, and lists?
Yeah, that was before I knew about NumPy. So
yeah. Fantastic. And Haran, what was your first line of Python?
Yeah, it's not going to be very interesting, but I remember the exact line was print hello world. But that was like 2012 maybe.
2012. So Haran starts off with the task that you know you can do, and Andy's over here saying, I need to convert my VBA tasks into Python programs. Awesome. Tanny, what about you? The first line of Python?
I think it may have been just import NumPy as NP. I believe that that was one of the first libraries that I started exploring when I very much started my route with Python. I actually went through a handful of programming languages before reaching Python. I coded a lot on LabVIEW, MATLAB, and then I reached Python at the end. I also did a little bit of some of the other more statistical based code development techniques as well. But yeah, reaching Python, I had to retrain myself and remember my times writing in C, because now I had to import my packages and they were not just ready to go like they are usually in MATLAB or LabVIEW.
Yep.
It was a fun experience, and I think having that previous experience with C definitely helped in just from the get-go to how to use Python.
Yeah, so Tanny, it sounds like you've always been about which language is going to give me some very fast arrays that I can work with. I'm curious, what about, did you, right off the bat, did you like NumPy more than what you were working with in MATLAB at the time? Or were you, when you first started with Python, were you thinking, you know what, MATLAB does arrays way better than NumPy?
No, I think in terms of speed itself for performance, I found them to be very much alike, and I quite like Python a lot because I felt like it got me further prototype-wise. I think what I struggled honestly the most when I just started with Python, coming from a MATLAB perspective, was the visualization of steps. Because in MATLAB, visualization is a lot more intuitive. I'm going to say everything kind of like comes out of the bat. And in Python, in this case, it takes just a couple more lines of code, but it's also very flexible and there's a lot more control about how we would like to visualize something. So I think as an introduction barrier, I did have a little bit of a struggle, but after getting to know the tools itself, I actually will very much prefer to code that on Python in order to visualize something and being able to publish it correctly. So yeah, I remember that being something that was a bit off when I started with Python.
Yeah, that makes a lot of sense. I have a little bit of a background in also MATLAB, but also R. And just working with R, I'm like, I would always think that this is so great, you know, for specifying models or having their formula syntax so convenient. But then when it came to do things outside of kind of the statistics realm, I was like, wait, why is iterating over, you know, a bunch of paths in a directory so cumbersome? And so that's what I really appreciate about Python, is it made some of the tasks that I was working with easier, and then I could kind of opt in if I wanted to do something computational. And then Hans, what about your first line of Python?
Yeah, I don't I don't really remember what that was. I mean, at the time when I was learning Python, it was on my own, so I didn't have a course. And I was playing around with it at the beginning for sure. So I don't know, probably automating some things with using Python as a scripting language.
Mhm.
When I started, I think not even NumPy existed. There was a precursor package that was called numerics. And yeah, at some point NumPy came around, and then I was starting to use it also for data analysis.
Yeah,
But that was
NumPy was,
when I was already doing my my master's thesis, or the German equivalent at the time of that.
mhm. Yeah, and NumPy really hit in combining a lot of different or features from different numerical array packages in Python. And from my understanding, and maybe you can enlighten us a little bit more, but once NumPy started becoming fairly feature complete, it did see like a very wide adoption to it.
Yeah, yeah, it's such a powerful paradigm to work with arrays instead of numbers. It leads to very simple formulas and simple code, and in most cases, let's say, and it avoids then this problem that we usually have in Python, that the loops are slow. So it was a really very useful and very
Mhm.
popular, successful package, and is today. I mean, people use pandas, but I stick to NumPy most of the time still.
Yeah. And I think Tanny and Andy, if you could also chime in, do you also stick more to NumPy than pandas? And Haran as well?
NumPy is my favorite, so I don't use pandas a lot. Just very, very specific things.
Mm-hmm.
So yeah, for me as well, in my grad research, I like to use NumPy because of the speed advantages it gives when you use like GPUs, for example. NumPy can be run in a way that's optimized for this. So I use that a lot. And when that was not enough, I actually just coded GPU for the GPU directly using CUDA.
Mm-hmm.
Yeah.
Fantastic. And then Tanny?
Oh, yeah, no, I was just going to mention as well that I think I agree. I think it also depends on what type of, what I'm really trying to do with the data. I think when it comes to, especially with machine learning algorithms, I think NumPy, or in this case, the tensors that come within the frameworks that we're using, are more of the standard. But data frames, I mean, in pandas are very much, very useful when it comes to having like a large data set that probably is not quite ready to go into a database, so there is no quite a need for it to go into a database. But then if I want to query it and I want to access it, and for it not to be a huge file as well, I think it comes very much in handy to use pandas. So I use them both a lot. It's just for different purposes.
Yeah. I'll typically write pandas for just tabular data, and then NumPy if I have something that's n-dimensional, where all my dimensions need to be full. Awesome. So it sounds like we all started somewhere using Python for some computation with a very heavy background in NumPy, maybe even NumPy being the reason we switched to Python. Okay. This will be our final round, programming as a superpower. It's a long trip from printing out hello world to actually being able to do something useful with Python or whichever programming language. But I'm curious, when did each of you realize how powerful programming can be? And so, Andy, we will start with you. How long between first picking up programming and starting to think, okay, I can actually do some things with this?
Well, I think I picked it up because at the beginning with this Visual Basic, because doing the task manually would have taken forever. But that was just the tool at the time. When I went to graduate school, I chose not to implement my workflows in C because I could one day analyze a data set. When I had to then realize I made a mistake after a year's worth of data, I really wish I had written it all in C. So that was a hard lesson to learn. Yeah.
Fantastic. And Haran?
So for me, I think even though I started pretty much at the same time as Andy, I was just using it for like fun. But one of the first things I did, like when I started using Visual Basic, this is before .NET or anything like that, but Visual Basic 6. And also before machine learning is a huge buzzword, I tried to write. So my native language is Sinhala. I tried to write character recognition program in Visual Basic, which was pretty much successful actually. So that was like the first time I realized, okay, this is what I need to be doing, just like programming.
You started feeling a little dangerous. Awesome. Thank you so much, Haran. Tanny, how about you? When did you first realize that programming is a superpower?
I think it was when I was getting closer to graduation during my bachelor's. And it's because, I mean, it's throughout my bachelor's, I had the opportunity to work on several programming projects. And I mean, they were all very fun to put together. I used many different programming languages for many of them. But at the very end is when kind of like a hands-on project came towards our group, and I was able to be involved with software-defined radio. That was way before my time in data science. That was when I was just mostly interested in digital signal processing. So we actually put together a radio frequency link that will be deployed actually somewhere, and I developed the code in LabVIEW at the time to connect to the link and collect the data and store the data somewhere so that we can analyze it remotely. And that was such a fun project to put together. I always felt so proud about it because I had a lot of help as well coming from many of my colleagues as well, a collaborative effort among our research team, but it was just so much fun to put together. And to see it actually deploy somewhere and be able to see the data, that was kind of like what sparked my interest in pursuing later on my graduate studies as well. That was kind of like my breakthrough when it came to programming, and I realized that I really liked it and what I wanted to do at the long run.
That is really cool. I love projects like that. I did something similar, but I'll save my anecdote for after Hans because I'm very curious. Hans, when did you first start thinking that this programming stuff is pretty cool?
Yeah, I mean, I still find it amazing that you can tell the computer to do something and it actually works. And programming is just that. I mean, you can push your tedious, repetitive stuff that on the other hand, you want to work exactly correct every time. You can push to the computer to do it for you. And the cool thing about a language like Python is you can really do everything. You can automate your tasks. You can write a graphical application. You can do hardcore numerical stuff on the grid, on the cluster, I don't know, on the GPU. So it's really a general purpose programming language. If you just know this one language, in the past you always had to have specialized languages for all these things, and with Python you can do all of that. It's really cool.
Yeah, I think it's amazing how we can all know Python, but we'll be in touch with very different aspects of it, usually through the use of different libraries, because we do all different things. And I think it's fantastic that one language can really support all of those different use cases and actually excel quite readily at those tasks too. But thank you all so much for sharing. This has been an amazing opportunity to get to know each of you. That brings our coding activity to an end. And so now, Hans, I would love to turn things over to you so that you can share your prepared remarks.
Yeah, the question is, so I don't know this software, so I don't know how to share my screen.
On the right side of your window, it's like a default image of a JPEG, or an image not found image.
Yeah, I think I got that. So let's see, I still have to give permissions. So I have to quit and reopen the app now. Sorry about that. We should have tried that out before.
All right. So in the meantime, while Hans is rejoining us, I'll share my brief anecdotes relating to Tanny's story. So Tanny, when I first started learning programming, I just joined a lab that used the MRI, or functional magnetic resonance imaging. And for one of the tasks that we had to do, I'd probably done Python for about 2 years. And one of the tasks that we had to do, we had to deliver tastes into someone's mouth while they were in the magnet. And so you can think, this thing, it has no metal parts, it's all plastic, but we also need some type of controller board that can actually drive a piston to then deliver liquid into someone's mouth. And I didn't know much about the any low level serialization or anything like that. So after a few weeks, I will admit, of tinkering, it was so amazing. I was using the script that I had written, and just to see like hit play or hit run on the code and see that piston actually change or actually drive, and I'm like, yes, we've done it. We can actually deliver tastes into people's mouths while they're in the scanner so that we can observe their brain, their hemodynamic response. Fantastic. That was when I first realized, I was like, wow, this is really cool stuff.
Okay, so yeah, hi everybody. I will talk about a library of which I'm maintainer and author. It's called iminuit. It's a library for fitting. So fitting is a thing you often do when you do science. But first, a bit about me. I mean, we talked about me a little bit, but I want to give you a bit more information as well. So I'm a particle physicist right now working with the LHCb experiment at the Large Hadron Collider in Geneva in Switzerland. But I was formerly an astroparticle physicist, and I was working then with the Pierre Auger Observatory in Argentina and the Ice Cube Neutrino Observatory at the South Pole. Yeah, I'm statistics convener in LHCb now, and I was before for 2 years, around the pandemic time. And yeah, generally my interests are, apart from physics research, are statistics, high performance computing, and API design. So all my whole philosophy is very well summarized by this quote from Scott Myers. We want to make interfaces easy to use correctly and hard to use incorrectly. And I really dislike using software libraries that don't follow this design, so I try to adhere to it in my own libraries. Yeah, I'm a member of the Boost project, so sorry, that's not Python, that's C++, where I maintain and wrote the Boost histogram library in that project. I'm also a member of the scikit-hep project, so that's a collection of Python libraries where I contributed iminuit, which I will talk about today, but also other libraries like resample, Jacobi. Now, Jacobi is not in scikit-hep, it's a personal library of mine. Similar with numberstats, you will see later. Then I also work on a larger project that's called Chromo, which is a front end to several generators that we use in high-energy physics to simulate particle interactions. And last but not least, there's a library called PyHapMC, which is able to read and write a standard format that we use to exchange records of these particle interactions when we simulate them. Yeah, and I also contributed to SciPy and Matplotlib. So let me quickly introduce what fitting is. So basically, you have a statistical model. What that is, I will tell you in a moment. And you have a data set that you just collected from an experiment. And you want to usually find model parameters that match the data best. And in the AI community, you would call this learning. And if you're coming from a classical background, you call this fitting. So your data set is usually consists of samples. So I put here like curly braces to indicate that this is a set. And the set can contain numbers or vectors of numbers. So vectors of numbers would be a multi-dimensional data set. If it's just one number, it's one-dimensional. And the values in your set can be continuous. So if you read off, I don't know, the voltage, that would be a continuous number. But sometimes your data can also be counts. If you make a counting experiment, for example, how many radioactive decays you have in 1 minute. Yeah, then the model in this case would be a probability density or probability mass function. Sorry, I have to use a little bit of math here, but I'm going light on math. So mathematically, that would be a function of this sample x and of some parameters which change how this probability density function looks like, the shape of it. And usually we want to know these unknown parameters p, given the data set. And there's a nice theory that tells us probably the optimal way of doing this is by using a maximum likelihood estimate, which is also sometimes abbreviated as MLE. And that tells us we have to maximize some function of these parameters. This function is called the likelihood. And when we maximize it, the point for which it is maximum is then the best set of parameters. And in principle, there are many, many ways in which you could probably think of how can I make my model match the data. There are many different ways of estimating the distance, so to say, of your model from the data. But the theory tells us that this maximum likelihood method is probably the best one. So for infinitely large data sets, this is proven. And for finite data sets that we usually deal with, we rarely have infinitely large data sets. It's not proven, but generally nobody challenged this. So nobody knows a better way of doing it, let's say. By the way, the likelihood is just the probability density function that I was talking about earlier, which you evaluate at each sample in your data set. And then you take the product of all of these things. So, I mean, in layman's terms, you just compute the probability of each of your samples and you multiply it all up. So it's kind of the global probability of getting this particular data set if F was the true model. Yeah, and the nice thing about this is you can always write down the likelihood for any problem. And so this technique works for any kind of problem. I'm telling you this because, yeah, I mean, there are also more specialized limiting cases to this, which you may know from your studies. So this is, for example, the least squares method, or the chi-square method, it's sometimes called also. That is more restrictive, not as general as the likelihood method. Yeah, and because I will not actually maximize the likelihood, but I will do something different in the following, I'm telling you that instead of maximizing some function, you can also minimize the negative of the logarithm of the likelihood, which is then called NLL for short. So that the formula is given here. So, I mean, you can make a maximum, you can turn a maximization into a minimization by just putting a minus sign in front of the function. And taking the logarithm of some function also doesn't really change where the maximum is, because that's a monotonic mapping. And that's why, yeah, this is the same. And for technical reasons, it's better to minimize the negative log likelihood instead of maximizing the normal likelihood. Okay, so to visualize this, I wrote here some Python code. So this is just generating a data set from the standard normal distribution, it's called, so also sometimes called the Gaussian distribution. So I mean, I don't want to go to this code here. Maybe just look at the plot with me. So the data samples here I illustrated with the small blue dashes. And then usually it's nicer to not look at this, but rather look at a histogram of that. So that's the shape in gray. The histogram is just counting how many times you have these samples falling into some bins along the x-axis. And then your model, here I put in the true model from which I actually sampled the sample. So I mean, in the computer I can do that. I know what the true model is and I can sample from it. So that would be this green line. The green line is smooth because this is a continuous distribution. The histogram is fundamentally a discrete thing because I'm counting things, and counting is a discrete operation. So the task would now be, how can I get from my sample back the parameters of this model if I don't know what the true values were, for example, for the mean and the width of this Gaussian. And if I want to get that, I have to first write my model down in a certain way. That is, I call this here model 1. So it's just a Python function. It takes an argument x, which would be my sample, and the two parameters from which this that define the shape of this model. It's a PDF, so PDF means probability density function. Internally, I just call here the normal distribution in PDF, which was already implemented by the SciPy library. But I nevertheless have to call it in a certain way, which is shown by this model 1 function here. It just happens to be look exactly the same. So in this case, could probably also skip that. Yeah, and this model I then use I have to construct a negative log likelihood as before to do my maximum or minimum likelihood fit, so to say. And this then it is a function only of the parameters that I want to know, which are mu and sigma. And internally, I compute my model PDF. I take the logarithm of that, then I get all the logarithms of all the probabilities. And before I told you I would take the product of all these probabilities, but now I deal with the logarithm of that. And the logarithm turns a product into a sum, so I actually have to sum up all these log probabilities. And then I have to use a minus sign to turn this a maximization into a minimization. Yeah, once I have that, I can visualize this. So, I mean, I told you before I have to find a minimum to get the best estimate for these parameters. So let's see graphically how that looks like. So I don't want to go through this code. This code is just plotting this function that I just showed you, giving the data set I just generated. And you can, on the left-hand side, see a 3D version. So the one axis here is the sigma parameter, and the other one is the mu parameter. And you can maybe spot by that there's a minimum of this function around a mu equal to 0 and sigma around 1. And the plot on the right-hand side is just the same function again, but in a top-down view as a color plot. Also here you can see somewhere the minimum is around 0 and 1. And if you want to know more precisely, then you would have to sample this function with a more fine grid. So you can solve this kind of graphically, but that would be tedious if you do it a lot. So it's better to just use a computer algorithm that does this in an optimal way or in an optimized way for you. And that algorithm is provided by this iminuit library. So iminuit is actually a C++ library underneath. And iminuit is a front end in Python to it. So you don't have to learn C++. If you want to use this library, you can just use iminuit. But under the hood, it's calling a C++ library. And this library is maintained by the CERN people that are also running the Large Hadron Collider, and more specifically the root team. Root is a large C++ software framework that is maintained by CERN. Yeah, and iminuit 2 is a code that was, it's a minimizer, so in principle you can minimize any function, but it was specifically designed for this task of minimizing negative log likelihoods and chi-square functions. It can also compute errors. So you usually in science, you want to know not only what is the answer, but also how precisely can we estimate the answer. And there are always some kind of sources of uncertainty. And this code allows you not only to get the best estimate, but also an estimate of how accurate that estimate is. So you can, it gives you a lot of freedom, so you can write your own functions to minimize. I call them quite generally cost functions as an umbrella term for the negative log likelihood and the chi-square function. And you do that in plain Python. Also, it gives you nice looking displays in a Jupyter notebook, as you will see in a moment. So applied to our problem here, I have to first import the iminuit object from the iminuit library. So that's what the first line does here. Then I have to pass in my negative log likelihood function that I wrote before. I have to give some starting values. So here I'm cheating a little bit. I already give in the true values, which I know in this case, but in general, I would just use some numbers that are close to the true values that I maybe know, or maybe have to guess. Then I have to tell iminuit that what I'm minimizing here is a negative log likelihood. So there's error definition. If it was a least squares function or chi-square function, then I would have to use a different parameter here. But for a likelihood, I have to pass this. And then I call the actual minimization algorithm, which in iminuit is called migrad. And the output of that is then displayed immediately here by Jupyter. So it found some value of that function, which is not really interesting for us. It took 32 iterations to get there. Then all these green things here, they tell you basically everything went fine. So if this is not green, then there's some problem which can happen. More interesting is then the table here, which shows you the value that it found and also the errors. So it immediately gives you also the uncertainty estimates for those numbers. Yeah, and as you can see, maybe you remember or you were quick in reading the code before. So the true distribution had a mu equal to 0 and a sigma equal to 1. But when you sample one specific data set from this distribution, you don't get exactly those numbers back. Because it's a finite sample, you always be a little bit off. And that's why these numbers are not exactly 0 and 1. And that is also then quantified by this uncertainty here. So within these uncertainties, the mu value is actually compatible with 0 and sigma is compatible with 1. Actually, there's a bit more than 1 sigma, as we say. So more than 1 times this error, we are away from 1 here. Yeah, and the last thing is a covariance matrix. So that's also an error estimate, but in a different form. Okay, so that's basically what iminuit does at the fundamental level. And then together bundled with this library is a library of common cost functions. So the negative log likelihood function is in there already, so you don't have to write this yourself. For the unbinned case that we just looked at, I will go into what unbinned and binned means in a moment. You can also have bin data, then it comes in form of a histogram. So for that, you need a different kind of negative log likelihood which is also provided by the library. Then in particle physics, we often want to fit not only the shape of our model, but also the amplitude of the model. And for that, there are, again, specialized functions that are called extended unbind negative log likelihood and extended bind negative log likelihood. Then in particle physics, you also sometimes don't even have parametric models. So before I was showing you, I could write down the PDF. It was coming from SciPy, but in the end, it's some kind of formula. But you may also have a model where you don't know the formula for, and you just have the Monte Carlo simulation that gives you the shape of this probability density function. And you can also fit those with a specialized cost function that's called template in iminuit. Then also sometimes you cannot always constrain all unknown parameters from the data set itself. Sometimes you also need to constrain them with some kind of external information. This you would do by adding so-called penalty terms to your cost function. And this is also supported with this normal constraint object. And last but not least, you can also do a least squares fit with iminuit if you want to. Then SciPy also has some minimizers in them, which work differently. And they bring some new features to the table. For example, they can be applied to constrain problems, for which iminuit and minuit, the minuit underlying C++ library, doesn't have a solution. So iminuit also wraps these minimizers, so you can use the same interface to call the SciPy minimizers if you like. And it provides some interactive fitting widgets when you use them in a Jupyter notebook. This is how this looks like. So here I now import my minuit object as before, and don't write my negative log likelihood function myself. I import it from iminuit.cost. I still have to plug in my model here, so this I always have to write myself. Yeah, and then if I use this instead of my self-written negative log likelihood as before, then I get some nice features like this automatic visualization of the fit, which I can then use in this interactive mode. So when you set your initial parameters and you give some limits for these parameters, and then you can call this interactive method on the minuit object, and you get this panel here, and there you can change mu and see how the shape then of your PDF changes. You can also change the width parameter, make it sharper. This unfortunately flickers a little bit. It works better when you do this in VS Code. And you can also hit the fit button here, which then does this calls migrate basically and gives you the best estimate of that. If you look closely, you can see that this value here, which is basically the function or the function value that the unbind negative log likelihood function returns, it's the smallest when we are here at this position. When I go away from that, it always grows, becomes larger. That's what we already saw before when I showed you this 2D visualization of the function value as a function of mu and sigma. So the fit really finds the smallest value here, and I just have to click the button to get there. Okay, so you don't want to do this by hand. This is just useful sometimes to understand what's actually going on. If you have this very complicated PDF and many parameters, sometimes you want to see what exactly is going on and whether you programmed them correctly. So that's what the interactive mode is for. But normally you just want to call migrate and let the thing do its magic, as we have done before. And when you use the built-in unbind NNL object instead of your handwritten one, then you also, as the output of minuit, you get this plot immediately. You don't have to write this plot yourself. Okay, so to recap, iminuit computes not only the minimum of, doesn't only give you this parameter estimate, but also the errors. You can compute them with two different methods. One is called Hesse method, the other one is called minus method. The Hesse method produces symmetric error intervals, we say. So it's basically the value plus minus and then some value and a covariance matrix. That's if you have more than one parameter, you can write down a covariance matrix, how they change together, basically. That's what this matrix quantifies. The MINOS method, on the other hand, produces asymmetric error intervals, and you can compute 2D contours. I will show you in a moment what this means. So neither of these two methods is superior, and if you are in doubt, then you should use the Hesse method, unless you have very asymmetric errors. So this is how a contour looks like. So sometimes people want to know, want to give not only an interval for each of these parameters individually, but a region where we think that most likely these parameters are. Like I said before, so when you compute your estimate on a specific data set, you don't really know what the true values are. You can just say, my estimate is here and it has certain uncertainties. And the contour goes in a different way. So in a similar way, you don't even, sometimes you just want to pick a region where most likely the true values are. And that's what this contour tells you. And in the statistics languages, we usually want to report what's so-called 1 sigma, 2 sigma, or 3 sigma contours. And this is why I pass here CL equal 1, 2, 3. This is what this produces. It's making iminuit produce these three kinds of contours, and they are shown here in the plot. So the 1 sigma contour mathematically is so constructed that it contains the true value in 68% of the cases. So if you would repeat this experiment many times, and you would always make this contour, then in 68% of those random experiments, the true value would be inside this inner contour. And then there are other well-defined probabilities for the other two. So you don't really have to worry about this unless, some point when you want to make a paper and publish, they ask you for this sort of thing. So iminuit is not the only kind of software which does this kind of job. There are also other Python libraries that I want to briefly mention. So one is called PyHF, which is also from scikit-learn, of which I'm also a member. So PyHF is a good library when you need to compute so-called limits. So you try to make an observation of a rare process, and you find you don't find evidence for this. Then you want to give an upper limit so that the next experiment doesn't have to look for it again, only if it's more sensitive than your experiment. So this is basically what a limit then tells other scientists. And they also want to preserve all the information from searching for this limit, which is encapsulated in the likelihood itself. And you can actually preserve the likelihood in a way that other researchers can make use of it. And for that, you should use PyHF. Then in Python, there's another library called ZFit, and in C++, there's a library called roofit. Roofit you can also use from Python, by the way, because the root framework, in which this is a sub-library, also has Python bindings. So these two frameworks, they also allow you to fit models to data. They help you in particular to build these statistical models, and they have nice features like automatic normalization of your model and convolutions. If you want to use these features in iminuit, you have to do that by hand. So by writing proper Python that does these things. So it's not automatic. On the other hand, so these are good for solving some standard tasks, but if they also restrict your freedom. So if you are like me and you want to experiment around and you want to use new techniques and combine different libraries from different projects, and these usually make this hard or impossible. iminuit, on the other hand, is different in that regards. It's very flexible, very open. It can be very fast. I will show you in a moment, and it has a modern API design and very good documentation. So, as I told you, I like speed, and why I think speed is important. So when you do a fit once, it's a small data set, and it's fast enough. You don't have to care about it. But sometimes you want to fit a very large data sample, and then the fit can take minutes if you don't write it in a specific way. And it's a big difference if you need to wait 5 seconds or 5 minutes for something to finish. If it takes 5 seconds, then you're much more likely to play around with the fit a little bit, to change things, to make optimizations, to maybe also use advanced techniques like the bootstrapping if you're not satisfied with the uncertainties that iminuit produces, which are not always correct. So there are situations where you can't just use the Hesse errors, and you need to use the bootstrap, for example, which is computationally very expensive. You have to fit the same thing many, many times. Or if you want to study systematic variations, so you have some parameters, you don't know exactly what the value of them is, and you want to see how your estimates depend on these parameters. Then you want to fit many times, and then it's important that it's fast. So some performance insights here for you. So iminuit itself doesn't really require a lot of time, so you don't have to worry about optimizing that. The bottleneck is really evaluating your cost function. Your negative log likelihood is the bottleneck. So you need to make that fast. Then the fit is fast. And more specifically, inside the cost function, the bottleneck then is the evaluation of your probability density function that you have to write yourself in iminuit. The good news, on the other hand, is this whole calculation is trivially parallelizable. So because you evaluate your PDF, your probability density function, on many, many values, and all these calculations are independent, so they can run in parallel. There's no synchronization between these calculations. So this means you can exploit special instructions by your CPU, which are called SIMD, so single instruction multiple data, and you can also parallelize on different cores of your CPU. So let's look how this would look like. So this is a little code that I don't want to go into detail again, which just generates another data set. So now it's a little bit more complicated than before. Before I was just generating some Gaussian distributed data. Now it's Gaussian distributed data, but also mixed in some exponentially decaying data. That's a typical scenario we have in high-energy physics. We want to know what is the integral, so to say, of the Gaussian part. So we have to somehow subtract the exponential part, and you can do this with a fit. So now we have to write our model again, and now we do the first thing to make it fast. So instead of using statistical distributions from SciPy, I now import them from another library that I also wrote. It's called NumberStats. It just provides a similar API, but it has much faster implementation. So what I do here is I now have more parameters. So one is called Z, that is the mixing factor, so to say. If Z is 1, then it's all signal, and if Z is 0, then it's all background. Sorry, background and signal is a typical language in high-energy physics. So signal would be the Gaussian, and background would be the exponential. I will probably say that a lot. So yeah, and because we have more than one PDF inside this model now, we have the mu and the sigma of the Gaussian, but also a slope parameter for this background. So we assume we don't know any of these parameters. We have to all get them from the data. So our negative log likelihood, which I wrote again here by hand, now has 4 parameters instead of 2, but otherwise it's the same. So I compute my probability from the PDF. I take the logarithm of that, and I sum it, and I take the minus sign. So I got my negative log likelihood again. And when I put that in iminuit, it gives me the result. I have to give some starting values again. Now I don't give the exact correct starting values, and it still works. Everything is green. And yeah, it produces some numbers. The point here was this took 6.4 seconds. But here I didn't do anything. It's just normal Python. Let's see where we can make this faster. One way to make it faster is we can use the just-in-time compiler from a library called number. So I import number here, and number has a special kind of decorator. So this is a decorator here. It starts with this at, and decorator is basically a function that takes another function and modifies it in some way. In this case, what it does, it compiles it. So it translates the pure Python code into machine executable code that your CPU can run very fast. The code here is the same as before. I just have to, for technical reasons, I have to put it in front. Then here is where the actual magic happens. So I also use again this just-in-time compiler decorator, but now I give it further information. I tell it I want this code to run in parallel, and I want to use so-called fast math. So I don't want to use normal math operations, but faster versions of that. Yeah, and that's it. But otherwise, it looks exactly as before. And if I plug it into iminuit then, and it takes 9 seconds. That's not faster, it's slower. I mean, before it was 6.4, now it's 9 seconds. So did I tell you something wrong? Yeah, the thing is, when you run it only once, it doesn't work, because first time you run it, it also compiles the code, which takes a significant amount of time. But if you run it again with a different amount of different data sets, then you don't have to recompile the code, and then it runs very fast. So now it's only 1.1 seconds. So I just called minuit again with the same function. Now it was compiled already. You never see the compilation happening. It's done automatically. And the second time it's running in 1.1 seconds. So compared to the pure Python version, you are 6 times faster. How I am with the time?
We are just about at the tail end here. So any final remarks, Hans?
I could tell you more about bind fits and unbind fits, which also make things faster. But I will just skip to the summary then. So iminuit is a very versatile, fast, and easy to use library for fitting. It has, for many common use cases, already built-in stuff, so you don't have to write code yourself. Its emphasis is on having very good documentation, which I find very important, and it's very bug-free. The open design is nice because then you can really change things and play around with things. You can get really excellent performance out of it. I couldn't show you this, but it's actually comparable to C++. And also important for users, if you want to install it, it's basically C++ code, but you don't have to compile it on your machine. You can just install it from binary files that are provided on PyPI, so it's really easy to install. And I just released a new version that supports Python 3.12. So this is not accurate.
Fantastic. And ahead of the curve on the 3.12 support. I know that a lot of libraries are still trying to add that in or add that to their testing suite. I would love to invite back up our host panelists and open up for Q&A. We will probably have time for 1, maybe 2 questions. So if you're in the audience and you have a question, now is the time to use that Q&A widget on the side of your screen to let us know if you have any questions. And if not, Hans, I have a quick question for you. During your remarks today, you shared a lot about the iminuit having a modern API design. And I'm curious, how do you approach API design decisions?
That's mostly you should adhere to some principles. So it's also in morals, it's good to have principles, right? And in programming, it's also good to have principles. So you lay out, very good principles. They are formulated in a funny way, but they're actually very good. Are formulated in the Zen of Python. Do you know Zen of Python? So if you don't know it, if you open the Python interpreter in the terminal and you just write import this, then it will give out a little haiku or poem, or I don't know how you want to call it, which is basically just a set of nice design rules. And if you follow all those rules when you write the library, then your users will be very happy. Another way of summarizing this is with this statement that Scott Myers gives to summarize his philosophy. So I read his books. Make interfaces easy to use correctly and hard to use incorrectly. And that's a very easy thing to say, but actually very hard to achieve. You have to really think about how people might use your library and how you can make sure that they can only use it in the correct way. And using something that doesn't work is not even possible by design. So I don't know how to say what it would be. So if you design a cup which has no handle, then you can then if you want to lift it while it has hot coffee in it, it get burned. But if there's a handle, then you don't have to even touch the cup. And in programming, you can do something similar. You have to provide a handle. You have a cup that could have a hot liquid in it.
Yep. You got to be conscious of all of the impacts down the line, right? Maybe by designing a cup that didn't have a handle, you can't have hot coffee in it. Exactly. But Hans, we did get a question in the chat from Vipka. Any recommendations on where to get started binding C++ libraries to Python?
As a library to do that, to that binding, I like PyBind 11 a lot. So that's a C++ library. It has very good documentation. So if you just Google for PyBind 11, I mean, on the other hand, I mean, yeah, you have to know C++ already. So this library is not really easy. The code or the things, the features it uses in C++, they are advanced. But the good thing is it's a code generator for the bindings written in C++ itself. So any other library that I know which does this sort of thing, it generates some code, but then uses a kind of intermediate language again, and cannot speak fully all C++ and so on. So PyBind 11 is just the best. It's very efficient. It's very fast and the best to integrate into your library with the least amount of hassle down the road. And you can do really advanced things with it.
Mm-hmm. Perfect. Well, thank you so much for your insight on that, Hans. And I have to say, wow, this has been a fantastic exchange. I want to extend a huge thank you both to Hans and to our audience for joining us this month, as well as our host panelists, and Annie and Hiran. And I wanted to let our audience know, if you're not already signed up for our newsletter, make sure that you subscribe. The subscription link can be found on our website. And as a reminder, that's meetup.doepy.org. Or if you don't like receiving just one email per month, you can keep a regular eye out on that website for information about our upcoming exchange next month. Thank you all again for joining, and I hope to see you all next time.